Bismillahirrahmanirrahim. Assalamu alaikum. My name is Hulafan Wadbajo and I'm from the Department of BS Chemistry and my ID is 007. Today from the course of Analytical Chemistry, the topic on which I am going to present my presentation is pH, glass and electrodes. So let's have a look on the contents of my presentation, and it includes introduction, origin, construction, working principle, limitations, and at the last we will see the applications of glass pH electrodes. So moving towards the introduction of the glass electrodes or glass pH electrodes. So glass electrodes are ion selective electrodes that belong to the group of electrodes with a non-crystalline solid membrane. So glass electrodes are ion selective electrodes, and ion selective electrodes are electroanalytical sensors with membrane whose potential indicates the activity of the ion to be determined in the solution of unknown concentration. And glass electrodes are non-crystalline solid. They are made up of amorphous solids. We will see the construction of the glass membrane in the construction section of the presentation. So the next one is the origin of glass electrodes. The formation of an electric potential difference on a thin glass membrane in contact with solutions was observed by Kramer in 1906. So the method that describes the electric potential difference on a thin glass membrane in contact with solution was discovered by Kramer in 1906. This method was used for construction of a device for measuring the acidity of solutions by Haber and Kalman-Siewert in 1909. The method developed by the Kramer was utilized. It was utilized for the construction of a device that measures the acidity of solutions by Haber and Kalman-Siewert in 1909. And the next one is the construction of the glass electrode. So a typical glass electrode consists of four things. The first one is the glass tube. The second one is the internal reference electrode. The third one is the filling solution. And the fourth one is glass membrane. Here is a schematic diagram of the glass pH electrode. This is the glass tube, which may be made up of glass or plastic. And this one is the internal reference electrode immersed in the internal buffer solution, and this one is the internal or the filling solution or the internal buffer solution, and this one is the pH sensitive glass bulb or glass membrane. So we will see the construction of these materials in the following slides. First of all, the glass tube. A typical glass electrode consists of a glass tube which has two functions. First one as an insulator, and the second one it acts as as a container of the internal solution in which the internal reference electrode is immersed. The glass composition usually consists of three elements. First of all, alkali metals, second one bivalent or trivalent metals, and the third one is the silicon dioxide. So depending upon the pH range, for full pH range that is 0 to 14, the composition of the glass tube consists of silicon dioxide consists of 63%, and the bivalent or trivalent elements consist of 5 to 7%, 5% and 2%, that is barium oxide 5% and lanthanum oxide 2%. And alkali metal consists of alkali metals consist of lithium oxide and cesium oxide, and lithium oxide is 28% and cesium oxide is 2%. So depending upon the pH range, the percentage of the alkali metals, alkaline earth metals, and silicon dioxide is variable. The next one is the internal reference electrode. Here is we can see the diagram. This one is the internal reference electrode, and it is made up of a silver coated with silver chloride. So this silver chloride is an internal reference electrode. The next one is the filling solution. As we can see that the internal reference electrode is immersed in a solution that is surrounded by the glass tube and the glass membrane or the glass bulb, and this filling solution is 0.1 molar HCl solution. Uh, and therefore the internal solution should contain a fixed concentration of both hydrogen and chloride ions. In practice, for the determination of unknown pH value, there is no need to have the exact pH of the internal solution, but only to keep it constant. The next one is the thin glass membrane or the glass membrane. Its thickness ranges from 50 to 300 millimeter. So the glass electrode is constructed with pH sensitive thin glass membrane in the form of a dome, bulb, or somewhat flat surfaces at the immersing tip, fused at the end of the glass tube. So in the diagram we have seen that the glass membrane consists of a dome shape. So composition of a glass membrane is a glass membrane is composed of oxides such as silicon dioxide, boron oxide, phosphorus, and germanium oxides, and the oxides of monovalent or divalent metals, for example, sodium, lithium, potassium, and calcium. So the most common glass membranes are based on the silicon skeleton containing oxygen atoms around it, the silicon around or surrounding the silicon tetrahedron. So for the selectivity or the determination of the hydrogen ions, the membrane, the composition of the glass membrane is sodium is in the following percentage. Sodium oxide has a percentage of 22, calcium oxide has a percentage of 60%, and the silicon dioxide has a percentage of 72%. So depending upon the application, the composition of the glass membrane is variable, is changing with the application. So here is the schematic diagram of the glass membrane. This one is the dry glass body, and here is the gel layer, internal gel layer, and this one is the external gel layer. So the standard laboratory glass electrode is about 12 millimeter diameter by about 12 centimeter long. So next, moving towards the working principle of glass pH electrode, or how does a glass pH electrode works. So the internal filling solution is a buffered chloride solution of constant hydrogen ion and chloride ion concentration. As I stated in the construction section, the internal buffer solution has a fixed pH, that is zero point 0.1 molar HCl solution. So the hydrogen ion establishes an ionic exchange equilibrium with the inner glass surface to produce the phase boundary potential on the inside of the glass membrane, while the chloride ion establishes a constant potential with a silver chloride internal reference element, and hence the chloride and hydrogen ion concentration is fixed or constant. So for measurement, only the glass bulb need to be submerged in the solution of unknown pH value. So the ability of an electrode to respond to changes in pH is usually associated with the water content of the glass. So the surface of the glass bulb swells slightly when immersed in a solution, and a hydrated layer is formed as the water penetrates into the silicate network. Here we can see that when the tip is immersed, or the glass membrane in dome is immersed in the unknown solution, we have a hydrated gel layer. This dotted line shows the hydrated gel layer, and it is formed after the immersion. This layer seems to facilitate the movement of ions in the glass and lower the electrical resistance. So the thickness of the hydrated layer is from 50 micrometer. Hydrated glass layer is 50 micrometer thick, and the rigid glass or the dry glass body is 100 micrometer in structure. The potential at the external glass surface is developed as a result of ion exchange reactions with the solution in which it is immersed. So here is a diagram that describes the general glass body, or the dry glass body, which consists of zero point 0.1 millimeter in width from this side, from here towards this. This is the glass body or the dry glass body, and 10 nanometer towards the left side is the hydrated layer that is in contact with the external solution or the solution of unknown pH value. And towards the right side, it is the hydrated gel layer on the inner side of the glass membrane, that is in contact with the zero point 0.1 molar HCl solution. or the buffer solution. So in a simplified description, a proton transfer occurs at the phase boundary between the glass and the hydrated layer. An ion exchange equilibrium is established between the hydrogen ions in the solution of unknown concentration and the alkali metal ions in the alkali metal ions in the glass. So here we can see that the sodium ions in the hydrated layer move towards the solution of unknown concentration, and the hydrogen ions that were present in the solution of unknown concentration move towards the hydrated gel layer. So the potential of this equilibrium is depend on the hydrogen ion activity. One reason the hydrogen ion has the ability to pass the pass the phase boundary more easily than other positive ions and penetrate to the silicon oxygen network is its small size. So the glass structure must maintain anionic sites for the ion exchange. So silicon dioxide of greater than 50% by composition provides this characteristic. So the alkali metal ions with the glass move slightly towards one surface or the other, giving rise to an electric potential. As I stated in this diagram, the sodium ions move towards the solution and the hydrogen ions move towards the hydrated gel layer. So the movement of the alkali ions describe the electric potential. This potential difference between the two sides of the glass membrane is proportional to the difference between the pH values on both sides. So uh, uh, as since the internal solution has a fixed pH value, and also the fixed internal hydrated gel layer. So the external glass membrane gel layer or the hydrated gel layer is different from the inward. So the potential difference, the potential is also different. So the potential difference between the two sides is responsible for the changes in the pH value of internal solution and also the external solution of unknown pH. So the glass electrode is attached to the indicating electrode terminal of the pH meter, while the external reference electrode is attached to the reference terminal. So in order to measure the pH of the unknown solution, the glass pH electrode is coupled with the external reference electrode. When both the electrodes are immersed in the solution of unknown pH, and they are connected to the pH meter, the pH of the unknown solution is described or displayed on the pH meter. So these were the working principle. This was the working principle of the glass pH electrodes. Now moving towards the limitations in the measurement of the glass pH electrode. So for the first one is the asymmetric potential. This is a residual potential between the two glass membrane surfaces when the solutions on both sides are identical. As we have learned in the construction section, that internal solution has a constant pH, while the external solution has unknown pH. So in this asymmetric potential, there is a condition in which external solution while the internal solution both are identical, but they have residual potential in the residual potential change. If both sides of the glass membrane are in contact with solutions of identical pH but develop potentials which are different, this condition is the asymmetric potential. This potential difference is normally a few millivolts. So what causes the asymmetric potential to rise? Any influence which alters the composition and ion exchange properties of the glass can cause asymmetric potential. So the composition and the ion exchange properties of the glass influences the asymmetric potential to be occurred. The magnitude of this potential varies with the pH of the solution in contact with the glass age, with temperature, and with time. So in order to remove this asymmetric potential, the glass electrode is stored in a soaking solution so that the glass membrane does not dehydrate. The asymmetric potential is likely to be remain constant. So the next one is the sodium ion or alkaline error. The sodium error is the result of sodium ions penetrating into the silicon oxygen network and causing a potential response. As we see in the construction or the working principle section, the hydrated gel layer consists of sodium ions that move into the solution, and the hydrogen ions from the solution into the hydrated gel layer. So the movement of the hydrogen, or the activity of the hydrogen ion, is responsible for the potential difference. So in the sodium ion error, the capability of the membrane for responding to other cations beside the hydrogen ion is also likely be possible. As the hydrogen ion activity becomes very small, these ions can compete successfully in the potential determining mechanism. Although the hydrated gel layer prefers protons, sodium ions will exchange with the protons in the layer when the hydrogen ion activity in the external solution is very low. So when hydrogen concentration is low, the sodium ions replaces their position in the hydrated gel layer and causes the potential increase or decrease. So this is occurring in the sodium ion error. The next one is the acid error. The acid error is different from the alkaline error in that it changes very little with temperature and is negative error, where a greater number of millivolts per pH unit is observed. At very low pH values, that is less than 1, pH values less than 1, the gel layer of the pH sensitive glass membrane absorbs acid molecules. This absorption decreases the activity of hydrogen ions and result in a lower potential at the outer membrane and phase boundary that is in contact with the unknown solution. Concentration of the solution. The pH measurement therefore show a higher pH value than the actual pH value of the sample solution. So this becomes in the acid error. So the correction of sodium ion error and acid error includes that the error in the alkaline solution requires a positive correction that is add to the observed pH value, whereas the acidic correction is negative. So moving towards the application of the glass pH electrodes, uh, before I start that describing the application, I would like to tell you a thing that all the applications of the glass pH electrode are based on the construction or the material of the glass electrode, either in glass membrane or the glass tube, excluding the pH measurement. So moving towards the applications, glass electrodes are used for pH measurement. As I described in the working principle section, when we couple the glass electrode with a reference electrode and potentiometer or the pH meter, we determine the pH of an unknown solution. So the next one is the specialized ion sensation. There are also specialized ion sensitive glass electrodes used for determining the concentration of lithium ion, sodium ion, ammonium ion, and other ions. Depending upon the, this is all again, as I stated before, this depends upon the concentration of the glass tube and glass membrane. So the next one is the field use and plant sample. pH electrode used for the field used and plant samples should have an epoxy body for added durability and be polymer or gel filled of or easy maintenance. So these types of electrodes are used for field use and plant samples. For laboratory use, the electrodes are suitable for general. All types of electrodes are used for the laboratory purposes, biological and pharmaceutical use. The electrodes with the electrodes with the Ross and double junction, that is double junction silver chloride reference, or tris compatible, are used for the biological and pharmaceutical uses. Food and beverage applications. The pH electrodes consisting of a flat tip and Ross or double junction silver chloride reference, or a spear tip for parsing samples, and a Ross or double junction silver chloride reference are used for food and beverage applications. Petrochemical and non-aqueous applications. The glass electrode flow and open junction to prevent clogging are used for petrochemical and non-aqueous applications. At last, the industrial and chemical applications. So the glass electrodes having a sure flow and glass body that is damaged from the sample uh, are used to in the industrial and chemical application. So this was all from my side. Thank you.